We're going to start with just a little review together. It says give the names for the parts of circle E. Because they call it circle E, we know that E is the center, and so ED, that segment, is the radius. And BF, since it goes through the center, then would be a diameter. AG is just the segment that goes from A to G, and so that would be a chord. But then if it's line AG, the entire line, that's when we call it a secant, or a secant line. HD only touches the circle at one point, at point D, touches the circle being a tangent line. Segment HD is just part of that tangent line, so we call it a tangent segment. Point D is the point where it touches, so that's the point of tangency. Angle FED has the center at the center of the circle, so that's called a central angle. Angle FBC has its vertex on the circle, so that's called an inscribed angle. Now we've got those curvy arcs going on. If we just go from A to G, that's a minor arc. Less than half the circle. Arc ABG means we're going to go from A to G, but we're going to pass through point B along the way. And that's the only way to get from A to G on the circle, by passing through point B. So that is a major arc over half the circle. And finally, BCF, if we go from B to C to F, BCF is exactly half the circle. We call that a semicircle. Let's talk about angles next. Here we have a radius that's meeting up with a tangent line. And we learned that a radius always meets a tangent line at a nice 90-degree angle, if that's a right angle. Here we have an angle where the vertex of the angle is the center of the circle. We call that a central angle. And how is that related to the measure of the arc? We say that the central angle is equal to the measure of the arc. Now when the vertex of the angle is on the edge of the circle, then we're just going to look at that inscribed arc, and we know that the angle is half the arc. Or we can say angle equals arc divided by 2. On the next one, I'm not sure which angle we're supposed to look at, but I assume one of these K angles. And actually, to find the K angle, we're going to have to know the measure of this arc and the measure of this arc. Since the vertex of angle K is inside the circle, the measure of that angle is equal to the average of those two arcs, arc plus arc divided by 2. Now we've got an angle with its vertex outside the circle. We're still going to look at two arcs. It's going to be this arc and this arc that are intercepted by that angle. And so when the vertex is outside the circle, we say the angle equals the arc minus arc divided by 2. Now we're going to talk lengths. So here we have a radius, and we have some measurement of a tangent segment. And how do those relate to each other? Remember, that's a 90-degree angle, so we're going to wind up using this triangle, using a Pythagorean theorem. Maybe I'll call this side C, since it's the hypotenuse of that triangle. So always the radius squared plus the length of the tangent segment squared will equal that hypotenuse squared. Just the Pythagorean theorem. Remember that part of that hypotenuse is the radius. So radius plus that outside part would make up all of the hypotenuse C. Here I've got two chords that are intersecting. Maybe we'll label them as A and B and C and D. So those little chunks of those chords, the A times the B always equals the C times the D. Looks like I have a secant line here, some of it inside, some of it outside. And I've got a tangent segment here, I'll label C. And remember, the formula we follow is outside times whole, the whole thing being A plus B, equals outside times whole. You could write c times c for that tangent, or you could write c squared, since the outside is the whole thing. Same idea for this last one. We've got an outside and an inside, and an outside and an inside, since they're both secant lines. So we are going to say outside times whole, remember to add, equals outside times whole.